Hello and welcome to this Chemistry World webinar, Unlocking the Future of the Chemical Industry, the Transformative Potential of Biocatalysis. I'm Natalie Starkey, Chemistry World's science media producer, and I'm here with you for the next hour, where we'll be hearing from three scientists asking important questions about the use of biocatalysis in industry. They're also here to answer any questions you have about the topic, and I'll tell you a little bit more about how to do that in just a moment. But before I introduce our guests, I thought you might be interested to read more about the topic of today's webinar. The webinar itself was inspired by a recent Chemistry World article focusing on the collaboration between and the work of our three guests, which is published in two papers you also have links to on the screen now. So feel free to bookmark those links for later because they're well worth a read, and we'll also share them in the chat so that you've got the links directly. Now, we'd really like to thank our sponsor, Johnson Matthey, for kindly sponsoring the webinar today. As a global leader in sustainable technologies, Johnson Matthey apply cutting-edge science to create solutions for customers that make a real difference to the world around us. They've been leaders in their field for more than 200 years, applying unrivaled scientific expertise to enable cleaner air, improved health, and the more efficient use of our planet's natural resources. So thank you again to them. And I'm delighted to introduce our webinar speakers. Our first speaker today is Fabrice Gallou, who is in the Chemical Development Group at Novartis Pharma. Fabrice received his PhD from the Ohio State University in the field of natural products total synthesis. After Fabrice, we'll hear from Harald Gröger, who is a full professor of organic chemistry at Bielefeld University in Germany. Harald's research focuses on the application of enzymes as catalysts in synthetic reactions, with a goal of fulfilling the criteria of high efficiency, sustainability, and scalability. And then we'll hear from Bruce Lipschutz, who is a distinguished professor of chemistry at the University of California, Santa Barbara. His research has shifted towards green chemistry with a specific goal to get organic solvents out of organic reactions using the concept of designer surfactants. Now, before we begin, I just wanted to let you know that, as with all Chemistry World webinars, this session is interactive, which means you can ask questions about any aspect of what's covered in today's event. So please use the questions box to send in your questions as soon as they come to mind, and I'll be able to see those along with the team from Chemistry World here, and I'll be able to put those to you in the live Q&A towards the end of the webinar. You won't usually be able to see other people's questions in the box, but don't worry because we can. So we will be getting them. Don't worry if you can't see anyone else's. But without further ado, I'd like to hand over to our speakers. And as I said, Fabrice is going to be first. So welcome, Fabrice. It's lovely to see you on camera. I'll let you begin.
Thank you very much, Natalie, for the invitation and a very kind introduction. So, as mentioned, it's a pleasure to have a chance to interact with you all, and it will be a pleasure to go through the journey we started a few years ago with Bruce and Harald in the context of a review article published about 2 years ago around merge catalysis, and we were focusing at the time on bio and chemocatalysis, and in the meantime, we also collected some very meaningful insight from practitioners, which was the content of a follow-up paper that came up afterwards. And so without further ado, let me start first with the first piece around the chemocatalysis. You can go to the next one, Chris. And in this first part and in the rest of the talk, the focus will be around that second paper, that perspective that we published recently into green chemistry, where the focus was really there around the various aspects, whether technically, you can go to the next one, Chris, where we focus on technical aspects, strategic aspect, external aspect around the ecosystem, and cultural ones, and depicted I would say the challenges linked to the use of biocatalysis, especially, and its merger with chemocatalysis, and how this penetrated or not the various industry, chemical or pharmaceutical or agrochemical industries. But today the focus will be really around purely technical aspect for the sake of time. So next slide, please. So why this first of all, and why the focus on medium, which would be the focus of today's talk also. There is a reason. I mean, you can see from this chart that starts today, but the picture has not dramatically changed over the years. Most of the mass utilization in the industry is around solvents, whether organic solvent that we use to mediate, or to work up transformations, or the water itself that we tend to use routinely for workup. And that constitute more or less 80 to 90% of the mass balance. So you can see that there's a huge, I would say, a huge impact of this, and the choice or the proper or improper choice of the medium itself can have an immediate and dramatic impact on the overall footprint. It's all the more important as many of the solvents we tend to utilize, especially in the such industry as pharma or even agro, have certain physical properties and necessitate the use of certain polarity of the solvent, and especially the use of polar aprotic solvent that tend to suffer from reprotoxicity liabilities. Next slide, please. And so that indicates the urgency of looking for longer term and sustainable alternative to this. Without going into the detail of that slide, just to give you also some more insight as to why the focus has been around water, and that, as we will illustrate in the next few minutes, is when we conduct the chemistry, I mean, typically we pay attention to the I would say the major component and the major outcome of the reaction, namely the product. But what's also very important, especially in the context of sustainability and overall footprint, is the waste aspect. And one can distinguish the different type of waste. I won't go through the detail. You can find out a lot more in the two references I indicated at the bottom of that page. But essentially, that waste stream is particularly important, and especially one can see that the choice, especially of one or the other solvent or the choice for water, can have dramatic impact in terms of CO2 release on the outcome. There's essentially 1 to more orders of magnitude going from water where the water has been the input material has been properly designed, properly selected, to the use of an improper organic solvent. So you see an immediate benefit of using water in a proper manner and designing properly the overall sequence of event and the overall reaction condition. Next slide, please. So now, when it comes to I would say the technology of choice we will be talking about today. So to make a long story short, when it came to the catalysis, the chemocatalysis especially, we were particularly interested into substituting those reprotoxic solvents mentioned earlier on. And a long time ago now, we came across the seminal work by Bruce Lipschutz around design, benign by design surfactant. And I'm showing here, I would say the lead compound, the workhouse for a long time, TPGS 750M. That's been maybe not the first one identified, but that's been the most described and the best understood up to now. And just to illustrate a few of the features by design, it's non-toxic. It's exhibited extremely rapidly a broad scope of chemistry with the exquisite selectivity, which was of particular interest. And there was reason for that. That was just the way the micellar catalysis function, inherently functioning under mild conditions, to which is associated high selectivity. And again, as part of the design itself, the compounds has biodegradability inherent to it, not necessarily the optimal biodegradability, but at least something sufficient to work around. Next slide, please. So let me just go through one use case, one vignette that will highlight the power of the technology. So I'll just illustrate how we could actually utilize the technology, and especially the chemocatalysis, to assemble an API. It's blinded, unfortunately, but it doesn't really add to the decoration of the compound. I think you'll get the point even by masking some of the functionality. So we were interested by this API, which, as you can recognize relatively rapidly, comes from a series of amide bond formation, SNAR, and Suzuki-Miyaura cross-coupling. Those are, by the way, the top 3 transformation to assemble active components in most of our industry, and especially in pharma. So very important type of transformation where we spend a lot of efforts. Next slide, please. And from the onset, we knew that there was a challenge with this chemistry, because we started from this dichloro pyridine, At least this was the original scheme, where the boronate ester of this dichlorpyridine was engaged into the cross-coupling with this bromoaniline. And even after some optimization, we could get the product. That was not so much the point, but you see the overall efficiency was relatively mediocre, plus minus around 50% isolated. And there was a reason. The main reason is the boronate ester itself has double functionality, not just serving as a nucleophile, but also can be further reacting. So we had the consecutive transformation that could happen, and they happened to a large extent, as you can see, and they accounted for this. And this was here, I would say, a balance between the reactivity and the selectivity, which led to these mediocre results. And from the onset, next slide, please. From the onset, we saw the power of the micellar catalysis by reducing the temperature to 40 degrees, which was feasible on the micellar catalysis conditions. We were able to get immediately plus minus the same outcome with much less catalyst already, which was clearly indicating the direction to follow. And one can start observing that already the selectivity starts improving dramatically. So we got essentially the amount of over substitution reduced by a factor 2. So continuing in this direction, next slide, please. We showed that, next one as well. We showed that by reverting the polarity of the system, we could continue getting better and better. In this case, we had to slightly increase the temperature up to 60, but we continued increasing the yield. So we got here more or less a complete conversion and an isolated yield around 95%, with only a couple of percent at most of the dye substitution of the product itself. Something I didn't mention as well, which is very important also in the context of sustainability aspect, is we could, with this micellar catalysis type of approach, go to a 1-to-1 ratio in the cross-coupling. So very important, as well as we minimize the waste and hence the potential for the challenges in the purification and isolation. The same happens with the catalyst amount, which got reduced, as you can notice. Next slide, please. And just by continuing this iteration of improvement and optimization, next slide, please, you see that by further designing and understanding the system, so in this case, by increasing the lipophilicity of the iodopyridine, we continued getting better. So here, this was not dramatic. The only thing that we really could achieve is that we could get the same reactivity by reducing the temperature to 45 degrees. And we started seeing improvement in the selectivity, so getting to well below 2% dye substitution. Next slide, please, which led us to continue the process of increasing the lipophilicity. Next slide as well, where we did the same trick, not just on the iodopyridine, but also on the boronate ester, and by capping the aniline. And then under those conditions, we had actually demonstrated this on a series of different catalytic systems, whether using the DTBPF ligand or the endophores, we could really go to very high isolated yield with hardly any over substitution, so typically well below 0.1%. Next slide, please. So this is just to indicate that essentially by the understanding of the micellar catalysis and the leveraging of this compartmentalization aspect and co-localization, we were able to decrease the catalyst loading, decrease and optimize the ratio and the mass utilization between the coupling partner, increase the selectivity, increase the yield, increase the productivity, because as the reaction becomes more selective, we can operate much faster and go through the cycle time much better. So which leads overall to a much improved outcome and footprint for this process step. Again, you can read more on the paper that is highlighted below. Next slide, please. So that ultimately we demonstrate we could put it all together. I'm just showing and focus here today on the most complex step, namely the cross-coupling, but utilizing the micellar catalysis and the chemistry in bulk water, we could essentially assemble the whole compound and essentially get to an overall isolated yield over 40% with extremely minimal amount of palladium catalyst especially, and all the steps were conducted with water as the bulk medium as mentioned. Again, more insight into the paper I was showing before. Next slide, please. And so this was it for the chemocatalysis part. Let me now hand over to Aral for the biocatalysis.
Thank you so much, Fabrice. Right, we've got Harold on screen now. Welcome, Harold. I'm going to hand over so you can continue with your presentation. Thank you.
Yeah, thank you very much, Natalie, and also thank you very much, Fabrice. Yeah, Fabrice already showed us the wonderful potential that chemocatalysis offers us also for applications in water. So we have numerous catalysts, which can man-made catalysts, chemocatalysts, which can be applied highly efficiently in water. And however, to make use of the full range of catalysts in general we also should not forget that there's another alternative class of catalysts which are also very interesting to be applied in organic synthesis. And these are enzymes, which are very complementary to chemocatalysis. And this would be my part in the next slide. I hope to show you that enzyme catalysis is not only a hypothetical option, but that it's a real, I would say, efficient and also technically feasible tool in industry, for industrial applications, for the preparation of valuable industrial compounds, in particular for compounds in the field of pharmaceuticals. What you see here is the industrial product tree. And this should illustrate that all over the, what we call product trees, or the starting with the low price but high volume chemicals in the plastics fields and materials fields, up to the high price, low volume area of fine chemicals, pharmaceuticals, enzyme catalysis can be applied. And I would like also to mention that often enzyme catalysis is translated as fermentation, which of course is also a very valuable tool. But also in organic synthesis, we can make use of enzymes as catalysts, similar like as chemocatalysts. So I think it's a really essential and important part, complementary part also in organic synthesis. This I would like to illustrate you in the next slide. I would like to start a little bit with an overview about organic synthetic steps with enzymes which are done on large industrial scale. And this list, this table shows you some very few selected examples. But it also shows you that it's not only applied on, I would say, on a kilogram or on a multi-hundred kilogram scale, but really on a very large scale. Probably the most, or one of the most largest applications is the glucose-fructose syrup. Of course, this is an isomerization of glucose to fructose by a glucose isomerase. So it's not maybe many colleagues would not regard it as a classic organic synthesis. But this is done on a 12 million ton scale, and it shows how efficient enzyme catalysis can be applied, because obviously this is a relatively low cost application. Then we have many applications in the field of chiral amino acids, of course, including also fermentations, but also consisting of enzyme catalytic applications. What you see here, aspartic acid, para-hydroxyphenylglycine, DOPA process. These are processes running on industrial scale with enzymes, so enzymatic steps, not fermentation steps. So you start from an organic starting material apart from glucose, and you transform this into the corresponding product. And that's true for many other amino acids as well. Acrylamide is a wonderful example that shows how efficient enzyme catalysis can operate. This is done on a multi 10,000, 100,000 ton scale. And of course, we have all the beta-lactam antibiotics, just to mention 6-APA, which is done on more than 10,000 ton scale using penicillin acylase chemistry. And then it comes more, I would say, to intermediate of pharmaceuticals or vitamins like methoxyisopropylamine or agrochemical in this case, which is, again, organic synthesis with enzymes. And now I would say, you might ask, what are the major application areas? I would say still today, already enzyme catalysis is a very matured field in the field of pharmaceuticals and fine chemicals. And according to my impression, when it comes to chiral building blocks, enzymes is one of the most favorite applications. And this I would like to illustrate in the next slide, which gives an overview. Very wonderful paper from Chemical Engineering News, even published a while ago. But on the left side, what you see in this table is that it's not only one enzyme class. There are many enzyme classes which can be applied, starting from redox enzymes, ketoreductases or alcohol dehydrogenases, to hydrolases, amine oxidases, transaminases. So it's a chemistry which actually is very difficult to be done for chemocatalysis still up to now. Namely, the transformation of a ketone into a chiral amine using a reductive amination process. Then CC bond coupling reaction, aldolases, and also halohydrin dehalogenases, oxidation by oxygenases. And I would like to also take into account one quote Within this article or citation, it says a lot about the maturity of biocatalysis as a synthetic tool, that 4 major drugs, Pfizer's Lipitor, Lyrica, and Merck's single-layer Januvia, are manufactured using enzymatic steps. So it shows that for very important pharmaceutical drugs on industrial scale, enzyme catalysis often turned out to be a key solution to get the corresponding desired Cara products. Next slide, please. Yeah, I would also like to mention, to illustrate now a bit more, going to the chemistry, some case studies or some selected examples with contributions from our own work in that field. And it should also illustrate the diversity you can address when you use enzymes, also in organic synthesis. What you see on the left upper part is a ketone reduction, and I would like to come that in a minute. But also, for example, the transformation of aldoxime to nitrile, what you see on the right side. That's a cyanide-free approach to chiral nitriles, actually. So something which is quite rare also when it comes to chemocatalysis, but also CN double bond reduction. Formation of heterocyclic amines can be done with enzymes very efficiently, or also hydrolysis that's shown on the right side, on the bottom, the example for the beta amino acid synthesis. And if you click one further, Chris, then now we see that, for example, 2 of these examples, the ketone reduction and also the beta amino acid synthesis, these are examples which have made it to industrial scale. And for me, both of these examples were really eye-opener. As a chemist, as an organic chemist, come into the field of biocatalysis during my industrial time. So actually something which I have not studied at the university. It was really exciting to see this potential that enzymes can be applied very efficiently and in a very competitive way on large scale. And due to time reasons, I just would like to pick out one example. This is shown. This is the alcohols. And Chris, please, the next slide. And this is an example which for me was very exciting, because at the time, that's already more than 20 years ago, at the time the industrial benchmark was, of course, the Noyori hydrogenation. So ruthenium catalysis with chiral phosphine ligands. And the question is, would it be ever possible to be competitive with an enzymatic catalytic approach to organic synthesis with enzymes? But I would just like to show that it's possible. And this list shows, I think this is in general true for any type of catalysis. It doesn't matter if it's chemo or biocatalysis. This is a kind of checklist about criteria which in the end decides if your process can be applied on technical scale, if it's economic, if it's sustainable. And of course, atomic economy plays a big role, sustainability. So Fabrice mentioned this already. The very important issue of reducing solvent, because of course solvent is a key contributor to waste in the end. Selectivity is a key issue, catalyst activity, stability, and economic access. And now you might say, okay, enzymes are expensive. This is actually not necessarily true. Enzyme can be actually very cheap. If you, for example, think about even what baker's yeast costs, and we often use E. coli, but it's the same way how it's produced. So it's a relatively low-cost approach to an efficient economic catalyst. In particular, when you take into account how much of metal costs, like ruthenium, palladium, iridium, rhodium, which multi 10,000 euros per kilogram. But of course, conversion yield plays a role. And a key issue is interdisciplinarity. This is also true for biocatalysis. You need to combine engineers, engineering techniques, microbiology, biology in general, and chemistry. If you go to the next slide. And now I would like to show you, this is for me, as mentioned, an eye-opener about the potential of enzyme catalysis. If you compare the reducing agent, for example, in a hydrogenation process, and you have the option of chemocatalysis and biocatalysis. Let's start with chemocatalysis. So Chris, UDC is, for example, a range of classic organic chemistry reducing agents. And if you would have one to pick out for industrial purpose, of course, probably you would choose, of course, hydrogen, because it's cheap, molecular weight is very low. So it's a very attractive reducing agent, without any doubt. And that's also why hydrogenation is served at that time, of course, as a benchmark. If you go, Chris, the next slide, please. If you go to biocatalysis, it looks a bit different. The reducing agent for nature is cofactors, for example, NADH, NAPH. And now, next click, please. If you look on the price of them, it might look like a mission impossible for biocatalysis to make it to industrial scale process. Next click, please. So let's look on the prices. Molecular weight of hydrogen to price very low, and the price is far, far more than 1,000 euro per kilogram of a cofactor. So obviously, what does it mean? It means that it will never be possible to use as hydrogen stoichiometric amount of a cofactor. It would be impossible to get a process. But however, that's the same process which nature had. And nature overcame this problem. Why? Because nature actually, also for nature, it takes a lot of efforts to produce a cofactor. So if you want to apply it in a cell, you need permanently to recycle the cofactor. So it's like a battery. It's like, if you go to the next slide, Chris. So in principle, the reaction formula is one equivalent of ketone, as you see here, plus one equivalent of the blue-colored cofactor, gives one equivalent of the alcohol and one equivalent of the empty cofactor, oxidized cofactor. So from this perspective, like a chemical reaction, you need one same stoichiometric amount of cofactor per the corresponding mole of your ketone. However, what you see here in the red frame behind is, next click, Chris, that if you have the option to recycle this cofactor during your reaction, you will not anymore need stoichiometric amount. You can use catalytic amount, very low catalytic amount. But what you need is a stoichiometric reagent which enables you to recycle this cofactor. But this can be a very cheap, non-toxic source like glucose. So that means now the reaction looks very different. It looks, next click, Chris. It looks that now you have 1 mole of ketone, which you see on the right side, the bottom, and 1 mole of glucose, which you see on the left side at the bottom. And glucose is oxidized to gluconolactone, irreversibly opened up to gluconic acid, highly water soluble. So it's in the water. You can get rid of it later on very easily. And the ketone is transformed to your desired alcohol. What makes this concept even more attractive, in general, the glucose oxidation step is irreversible. That means per 1 mole of glucose and 1 mole of ketone, you end up with 1 mole of chiral alcohol and 1 mole of gluconic acid. So it's a highly, and you can do this in water. So, and you can do it under very soft ambient reaction conditions. It's a highly attractive process. Now you might argue, okay, enzymes are expensive. But when you think about producing such and applying such a process on scale, what is the most attractive formulation of an enzyme? Of course, that's a whole cell, because the cell is the most early, of course, formulation of an enzyme directly coming out of a fermentation. And here we benefit tremendously of the opportunities in molecular biology. Today, we can design cells in which there is a tremendous high amount of the enzymes which we need. So in this case, the alcohol dehydrogenase, what you see on the right side, and the glucose dehydrogenase, what you see on the left side. That means by tailor-made microorganisms and producing them in the same way or similar way like Baker sees by high cell density fermentation, you have an extremely cheap, economically attractive catalyst now to do such a chemistry in water, and you get a chiral alcohol for a pharmaceutical, for example, by just applying 1 equivalent of glucose as a reducing agent. That's a wonderful process, and this also has made it then to industrial scale. Next click, please. And what you see here is you can add a very low amount, but you don't need it actually. Cofactor as an external cofactor. The whole cells are available by high cell density fermentation, and you can run reaction with very high conversion, more than 95% conversion. But most important, and often it's said enzyme catalysis, and of course nature has not made enzymes to make products with 100 grams per liter, but we can use enzymes to do so. And these processes, and this is shown on my last slide, these processes can be applied. So just by adding cells, just by adding glucose, and you can convert the ketone to the corresponding chiral product, high value chiral product with quantitative conversion and with substrate loadings above 150 grams per liter. So this is exactly the range which you would like to have it for fine chemicals, for pharmaceuticals. And this shows, for me, this was an eye-opener project. So I still like it, even it's a long time ago. And I really think it's encouraging to think about using enzymes as solutions, of course, besides also using exciting chemocatalysts as solutions to run reactions in water. And of course, the next logic step would be to combine it. And this will be introduced by Bruce.
Thank you so much, Harold. I'm just going to remind the audience that if, there's a lot of information to take in here. We understand we're going through a lot of content in an hour, but we are getting some questions in, so please do keep sending those in for once we've heard from Bruce. You will get sent a recording of the webinar within a few days, so if you want to go back and watch again, if you want to go over anything again, then you'll be able to do that. But I'm going to hand straight over to Bruce now to finish off with his part of the presentation.
Yeah, thank you, Natalie. And of course, at this point, as the slide indicates, we've now heard from Fabrice, who taught us that chemistry in water, chemocatalysis, is certainly possible. And of course, Harold now has hopefully convinced us that enzymatic catalysis, also in water, is very viable and very attractive technologies. So what I'm going to do is, as Harold indicated, is show everyone how one can actually use both of these, chemocatalysis and biocatalysis, and what we call chemoenzymatic catalysis, all in one pot, and of course all in water. And let me get to the punchline on the next slide, which is that the enabling technology here is really, as Fabrice alluded to, the use of micelles and the use of surfactants that therefore form the micelles. And what you're going to see is that by having these surfactants forming these micelles spontaneously in water, one has the opportunity to do this chemoenzymatic catalysis. That's really crucial to understand that, because oftentimes in doing enzymatic reactions, we run into the problems of enzymatic inhibition, sort of textbook processes that tend to be product dominated. But if we just have, as you will see, the micelles in the water, it provides an opportunity. It's sort of like the Hotel California, right? It's an opportunity for the product that normally would not want to go into the water because, of course, it's organic and insoluble, to go into the micelles, free up the entrance of other starting materials, which now can participate in the very valuable enzymatic processes that Harold described. So if we go to the next slide, I just show one example here of a biocatalysis reaction, or a series of reactions, which would not be possible if the first step, for example, using an enzyme reductase, and you can see the graph below, and I should point out that all of the enzymes that we at least are using are out of kits. So they're therefore sold commercially. You can get them from Johnson Matthey kits, Sigma, Codexis, etc. And we are obligated, therefore, to use them as indicated. But the point here, of course, is that doing an enzyme reductase on this particular enone, you see without the surfactant, the micelles being present in the water, is going to stop. It's just in the buffered medium, the aqueous buffered medium, it goes to about 45% and it just stops. Well, that does not allow us to do chemoenzymatic catalysis, or even a second step, which is biocatalysis, because nobody's going to carry 50% of the starting material through a series of reactions. So it's absolutely essential that we get a high percentage of conversion here, and that just translates into using a small percentage of an inexpensive, readily available surfactant. And now, as one gets up to 100, let's say, roughly 100% conversion, does one have the opportunity to do a second step in this case, which is using a ketoreductase, to generate this sort of 1-2 stereochemistry with any sort of outcome that one wishes, and that is enabled by the surfactant. So on the next slide, we see that there is an opportunity to use that surfactant. For example, with this highly lipophilic species, we're doing the same type of chemistry, but look at what would happen if you just took this enzyme right out of the kit. It's worthless in the sense that for this particular substrate, there's no conversion. You can see the blue line at the bottom with the buffer, there's just nothing there. Now you can add to weight percent. It's critical that people understand that that's 20 milligrams per milliliter of water. So it's not mole percent. Now these compounds, surfactants, weigh over 1200. So it's sort of there, but it's not there. And so adding 2 weight percent is kind of nothing. You can see how much we generate by doing that. And as the slide indicates, sometimes you just have to add more. And as you see, just by having it in the pot, for example, 6 weight percent, which is not much, you buy additional percentages. And so you can get this reaction to go from about 5% conversion up to very close to, let's just say 65 roughly % conversion in a very reasonable amount of time. And of course, as we will see, not only do we get the conversions that we're interested in, but the rates of the reaction are going to be enhanced as we shift this equilibrium by taking the products of these enzymatic reactions, localizing them in the micelles, and then of course have the opportunity for higher conversions. And inside the micelle, it's a hydrophobic pocket, so the product that one wants is localized within. But on the next slide is another example of how we can use different surfactants. It's important, as we will see, to screen the surfactants because they don't all work on every substrate the same sort of way in the sense of conversion levels. So here, for example, if we were to take the same substrate, and we already have seen that this doesn't go very far in buffer, and we've seen already from the previous slide what happens in TPGS. But we introduced last year the biodegradable surfactant, replacing the PEG with the polypeptide, as shown in the upper left, and that more polar medium, now as you can see, the rates are faster, the conversion level is higher, so in really 8 hours, one has maximized this out at about 65%. And what did you do? You just added it into the reaction mixture. You had an opportunity for that product, which would create this enzymatic inhibition, to now localize within the micelles, and the reaction goes much, much further. So on the next slide, we see that, in fact, you have to do, using, in this case, transaminase, a very quick study. You can get the answer to which surfactant is the best for your particular substrate in a day. This doesn't take a lot of time. These are just TLC experiments. You can see in the case of the transaminase, the reductive amination to this primary mean, right? In this case, it's most effective not using TPGS. It doesn't have to be ours. It could be any surfactant that seems to do the job for you, just having it in the pot. We're coming to the chemocatalysis part of it, but so far we're just doing biocatalysis, and we're having it in the water, and we're now taking advantage relative to the buffer. And in this case, it's not much, maybe 5 or 10 or 15% is what you'll buy, but it's free. You just have the surfactant in the pot, and you can see in the case here on the left that it's not necessarily TPGS. You go to the case on the right, and you find out that, gee, you can get 20% just by having a little bit of solutol in the water. So again, you have to screen the surfactants, and as we see on the next slide, here is now starting a series of reactions, because if you can get the conversions that you need to go pretty high, now you can start mixing the biocatalysis, and we already have seen the surfactants enable the chemocatalysis. So by definition, there are 2 reactions associated with chemoenzymatic catalysis, one which is mediated by enzymes, a bioreaction, and one which is mediated by some reagent, which we would call a chemocatalysis. But why do we have to stop at 2? Maybe we can do 3 or 4, all in one pot, all in water. This is now possible with the conversions by virtue of the micelles. So we've seen the micelles affect the biocatalysis, and we already know that the micelles enable the chemocatalysis. So let's do everything sort of together. Let's combine them. And so here, for example, we've seen the starting material before. We use an amine reductase out of the kit. We do a biocatalysis process in water enabled by the surfactant. We set up the stereochemistry next to the ketone. And then now in this particular case, we add an aminotransferase that sets up again the 1,2 stereochemistry, the absolute stereochemistry. And then we just take that material, do an SNAR reaction, and isolate in very effective yield, very good EE. And of course, the diastereomeric excess is a function of the enzyme, or enzymes in this case, and that's something that would vary by substrates. It's not so important here, but it shows you what's possible by doing multiple reactions in one pot. So on the next slide, let's take a look at now changing the sequence. We're going to do the same reductive amination, the aminotransferase chemistry, but you can see we can use that to advantage by taking, for example, a racemic benzylic alcohol, oxidation, I get it, Des-Martin pyridine, expensive, but let's just take it as a representative oxidation process. We don't have to isolate, we just now add the enzyme to the pot, do the biocatalysis, convert that efficiently into the corresponding non-racemic, in this case primary amine, and then we isolate as the CBZ protected material. So if you look at the overall transformation, you're taking a racemic alcohol to a non-racemic amine, taking advantage of both the chemo and the biocatalysis processes. On the next slide, you can see now using imine reductases, IRADs, right? So once again, it comes down to the screening in terms of the use of the surfactants. And here you see, for example, that using tween, readily available, inexpensive, for this particular reaction, of course, there's no chirality, but look at the difference between the buffer, not just in terms of what you buy in terms of isolated material, but look at the rate. Look at the rates of these reactions just by pulling that product away from the enzymatic pocket, right, just into the micelles. And so whether you use tween or TPGS or PTS, you, again, figure that out pretty quickly, but you can see you buy rate of reaction and you buy a high conversion. On the next slide, we can see again now using that type of chemistry, that is the biocatalysis using the amine reductase to generate secondary amines, let's start doing multiple processes, now in this case 4, in this sequence. So we take a carboxylic acid, we use our technology, no more peptide coupling reagents, byproducts that create waste in terms of ureas. We've done away completely with that. We make these thioesters just like nature does. We follow nature's lead. That's what nature does in the human body. We modify it, we generate. You can put it on the shelf if you want. It's perfectly stable. We just use it in situ, convert that into the desired amide as shown. And now comes the biocatalysis step. So out of a kit, we just add the corresponding IRAD that gets converted to the secondary amine, which we isolate as the CBZ derivative. 4 steps in this sequence, no problem at all. Next slide. So now let's shift the order, and very quickly, I think you're getting the point. You can do now, let's say, the imine reductase step, the reductive amination first. That molecule is isolated just by extraction, use crude, no purification. We convert it to the corresponding trifluorocetamide. Once again, we isolate that crude, and that's mainly dictated by the fact that certain IRADs have to be run rather dilute, while the chemocatalysis step is actually run at 0.5 molar or greater. But in any event, taking that material, we can do a Heck reaction with this particular iodobromide. And the point to this particular slide is not to then follow up with the Suzuki coupling, but to notice that this does not require any additional palladium whatsoever. So in a sense, this is what we would call metal economy, because palladium is in the pot already. Why not use it? Another virtue associated with chemocatalysis in water. Next slide. So here again is another sequence, but in this case, we're talking about esterification in water. Now, that's going to bother a lot of people. That's counterintuitive. How's that possible? It is possible. And we found a lipase, palatase 20,000, that'll do this esterification in water. We shift that equilibrium. This is all enabled, as you can see, by the TPGS. So what do? We take the carboxylic acid. We do, as we described earlier, a catalytic reduction in water. We then use the lipase, the biocatalysis step. We make the ester. We don't isolate it. We now use our technology, which we also developed, as you can see the reference, to remove the 2 bromines from the cyclopropane ring, because there are a lot of drugs that have cyclopropyl rings included. But the point again is you can mix these sort of processes, the chemocatalysis, the biocatalysis, all in one pot. Now on the next slide, and I think this is the last, one of the last chemical slides, you can see the impact on esterification. Now, I should point out that this is a one-to-one correspondence, as Harold pointed out. This is one equivalent of acid, one equivalent of alcohol done under this lipase condition. So just thinking about having the surfactant in the pot, it's a huge difference. You get 5% if you don't have that present. And what did it cost you to get 65, close to 70% conversion for this particular esterification just by having the TPGS in the pot? Now, could we do better if we went to 4%, 6%? I don't know. We didn't do that. Probably yes, but this is what we did do, and I think it makes the point. So what we tried to do in summary on the last slide is put all this together, as Fabrice mentioned, into that first paper that we published, I guess that now is really not that long ago, actually, where we combine, right? The magic ingredient is not to just have, in this case, the micelles present, but to recognize that we're doing all this chemistry in water. That's the take-home message. It sort of makes sense. Biology, biochemistry, enzymatic catalysis, essentially a water phenomenon. Why don't we do the same in terms of organic synthesis? And that's what hopefully we've convinced you is now possible. And then, of course, the combination. So I'll turn it back over to Natalie, and thank you all for participating. My thanks to Natalie, Chris, and Ada for organizing all of this. And I think at this point, Natalie, we're sort of ready to answer questions.
Yes, brilliant. Thank you. I'll welcome Harold back on screen as well. Brilliant. And yeah, thank you to Chris from Chemistry World in the background, sharing the slides and keeping up with the presentation. It was all beautifully presented. I think, you know, even as a non kind of pure chemist, I was actually able to keep up, I think, with most of that. That's been brilliant. We've got lots of questions coming in, so we've got lots of interest in the audience and everything that you've been talking about. I'm actually going to start with Bruce, as we've just heard you. I think we'll just start with a quick question for you. One of the questions is, since at least 2 reactions are involved in any chemoenzymatic process in water, and it's been shown that more than 3 can be done in one pot, does this extent of telescoping lead to purification problems downstream?
Yeah, that's something I oftentimes hear about. Thank you for that question, Natalie. What many people don't realize is those kinds of comments are true, but they reflect experiences associated with traditional organic synthesis. So if one is running a reaction which leads to some byproducts, and then you carry it through in the second step and the third step, absolutely right. There is going to potentially be a problem with telescoping. But one thing that people have to realize, and I think Harold pointed this out very effectively, is that these reactions, which include both chemocatalysis and biocatalysis, are run under very mild conditions. And the reason we can get away with this is because the concentrations, as was pointed out, are so high. They're 10 times higher than one normally would use in an organic solvent. So what I'm saying is, it's sort of like taking an elevator meant for 50 people, and we're shoving 500 people in that elevator. It doesn't take much to do chemistry in that elevator. So what I'm saying is, we don't see a lot of byproduct formation. It's this very different chemistry, very mild chemistry. We can do this chemistry without worrying about the byproducts and the separations. Yes, at the end, one has to do that, but it's really not anywhere close to what one sees when telescoping in traditional organic solvents.
Okay, thank you. Harold, I've got a question for you. To what extent can enzyme catalysis be competitive with chemocatalysis when it comes to industrial criteria such as high substrate loading and high space-time yield?
Yeah, so in general, this is also a classic, I would say, we just often hear that enzyme catalysis runs under very diluted conditions. But of course, this is also true for the past. So for many processes decades ago, for example, when you think of Baker's yeast, they run with 2 grams per liter and 100 of substrate and 100 grams per liter of Baker's yeast. But the reason is not because the enzyme is not good. The reason is because at that time, in a Baker's yeast, of course, as a native organism, nature has no tendency to overproduce one enzyme. This is what we want to have as a chemist. And actually, just to give you some numbers, so actually when you think about that an organism consists of, let's say, 2,000 enzymes, and that all, which is not true, but let's assume all of them would be produced in the same manner. You would talk about 1 divided by 2,000, 0.05% would be your enzyme in such a biomass. Today, by molecular biology, we can raise this up to 50%. So instead of 0.05, 50%. So nearly half of the protein is related to, I would say, to your specific enzyme you're interested in. That means with the same biomass, you have 1,000-fold catalytic power. And that means that nowadays we can run reactions, as Bruce also indicated very nicely, with 100 grams, even more than 100 grams, 150 grams, or even more per liter. And this is exactly what you need to do these high space-time yield to be industrial competitive. But this is reality. This is not just a hypothesis. This is actually reality. And the key issue is the combination of molecular biology and organic synthesis, and of course also engineering, so this interdisciplinarity. And that's why today I would say when it comes to industrial application for carbon building blocks, where of course enzymes have, due to their high selectivity, very unique properties, that's in this field, I would say enzyme catalysis is already a very matured industrial technology, and we should make more use of it. Yeah.
Yes, thank you very much. Actually, Fabrice, I had a little question, just stepping back a little bit from the science, about how the three of you came together to actually produce the survey and decide to work on this and kind of investigate what industry were doing and what they were thinking about this. And also, second part of that question is, did you see big differences across different types of industry as to the uptake of biocatalysis or the interest in it?
Yeah, so let me start with the first one. So Bruce and I have been interacting and working together for quite some time. So we've had plus minus for the more than a decade now, some recurring collaboration and topic to work on. And so we wanted to, we were invited to contribute to a ChemRev around merge bio and chemocatalysis. And Harald was invited by the same token, normally to contribute individually, but then we joined forces. So this was the first stage. And then while talking, we actually were quite ambitious. We wanted to do not just a literature survey, but complement this with I would say a pulse from the industry, the various type of industries, which we did. It turned out to be a little bit of a challenge to put it all together to fit the timelines. You know how this is. So essentially, we delivered at least the one story for ChemRev, but we wanted to finish up the very impactful and meaningful insight we got from the rest of the industry. So this is what we did in the second part. So more or less incidentally, we came across and worked together, and the chemistry among us worked out also very nicely. Now back to your second question, there is some specificities from industry to industry, also in virtue of the physical properties of the type of compound we're making. So especially in fragrance, for example, which is an industry where there's been a lot of attention around sustainability as well. This is a little bit different type of compound they're working with. But what we know is that at least agro and pharma tend to resemble each other, and so there's meaningful learning from one to the other industry in the space we talked about today. The chemical industry, the bulk industry also has more or less the same observation, although again, the kind of compound that they target is a little bit different, obviously, and the tonnage at the end of the day makes a big difference. As mentioned earlier on by Harald, the tonnage tend to dictate also the incentive, especially if there's some capital investment required. So the industry reacts at different pace depending on the needs and the requirement of their own specific industry itself.
Completely. And actually a follow-up question to that for any of you is much large-scale chemical production is already set up for high temperatures and pressures, and obviously they've invested a lot in that. So what changes would industry need to make to move to these new catalysts? And any of you can take that or jump in.
Can I start, if you don't mind?
Yeah.
So I start, and I'm sure Harald and Bruce can complement. First of all, this is a change, like you said, and a change is never easy. So this is one of the aspects we're describing into that perspective. So there is a cultural element behind. It's at the end of the day, it's a change. It's a change of paradigm, which means there's a barrier, and culturally it's difficult. So that's the first thing, first and foremost. But then what's remarkable, especially with this chemistry, is that there's no capital investment required with that. This is what we noticed ourselves. We've been engaged into this for almost 15 years now. With a few techniques that we've been describing, we can essentially go to any plant. There's a little bit of work up front, of course. You need certain experience and expertise to be able to develop things in the right way. But at the end of the day, we did not notice any requirements in terms of specific type of equipment, especially. So this is one of the additional benefit of the technology in my mind. So please, Bruce and Harald, feel free to complement.
Bruce?
Harold, he has the industrial experience behind him.
Yeah, I think I fully agree what Fabrice said, and maybe just to add maybe two issues. So one is also Bruce mentioned this before. When you want really to make an impact on sustainability, you have to address the solvent issue. And there's a very nice example apart from biocatalysis, which is Soloft. And just by reducing the number of workups, but keeping the same chemistry, the same steps, but doing all of them in one pot instead of one after the other, you could reduce the amount of solvent consumption per ton from 100,000 liters, around 100,000, to about 23,000. So by 75%. And I think this shows that if you are able to combine chemistry in one pot, multi-steps, that then you have a tremendous impact on the decrease of waste. But for this, you need to find compatibility between the steps. And if you have reactions which run at 150 Celsius degree, then of course you exclude reactions which operate at 20 degrees. So it's much better from a sustainability point of view to think about finding process windows in which all of these methods can operate at I would say, a reasonable reaction temperature around room temperature. This would be the ideal case, besides saving energy as well. And the other thing is, of course, if you go to high temperature and high pressure, you can do many reactions, that's true, but often at the cost of selectivity. And this is also something which we have to take into account. And the other one is in terms of resources, maybe to add that, for example, when you have a continuously running reactor for 100,000 tons scale product, and you need a expensive metal, you can recycle it over the years. But if you go in pharma, that's often the case, to relatively low volumes, 1 kilogram, 1 ton, 100 tons, something like this, it's actually not possible to recycle it 100 or 500 times. That means, for example, in enzyme cases, often the costs per kilogram of biomass are very low. But when you think about the costs of kilograms of a high expensive metal like rhodium or palladium, then often recycling becomes mandatory, which, however, if you talk about smaller volumes, it's also not economic. So also in terms of this issue, it's quite valuable to think about biocatalysis, but in general, I would say it's quite valuable to think about environmental friendly conditions and process windows, which makes it possible to combine reaction. And that means we have to take care about compatibility. Yeah.
Okay, thank you. I know Fabrice has to run out to another meeting very, very soon, so I'm going to ask one more question from all of you, and then I think we'll have to close for today, but it's been brilliant so far. A quick question from Roderick, who says they work in the field of green organic reactions, specifically in the field of multi-component reactions. Have you considered supporting enzymes on heterogeneous supports so that they can be reused? And that doesn't mean anything to me, so I hope that helps. I hope you're able to answer that question. One of you, anyway.
Well, I can tell you that it's coming. We're doing that right now. And
okay, brilliant. That's good to know.
It's a great idea. I think it's a missing link, in my opinion, at least in terms of what I see. Fabrice and Harold may have other comments, but as far as we're concerned, I agree 100%. And we are almost done with the first aspect of that, which will include exactly that, which is as part of a sequence, heterogeneous catalysis with mounted enzymes.
And maybe just to add this, there are two major, I think I always would fully agree to what Bruce said, and there are two major advantages. One is if you heterogenize systems, you can easier separate them from mixtures. And the other one, from a conceptual point of view, it's also exciting, because if you heterogenize two systems, it means it's easier to achieve compatibility because the systems don't see each other if they are embedded in a heterogeneous system. So in terms of compatibility and joint process windows, it's certainly fully agreed to Bruce and also to the comment. It's a very exciting option for the future. Yes.
Well, but one feature that we find is recyclability.
Yeah.
Obviously, you just filter it off, and we've shown, as will be coming, it's recyclable. The enzyme is recyclable.
This is good news then for green chemistry moving forwards. Thank you. That was a great question. Thanks to Roderick. And I'm really sorry if we didn't get around to answering your questions today. We did have quite a few in that I haven't had time to get to, but email addresses are on screen if you want to contact any of the speakers today. I'm sure they would be happy to be in contact with you. But yes, we've got through quite a lot, and I just want to say thank you to all of our wonderful guests today, for Bruce, Harold and Bruce, for joining us. I've certainly learned a lot, and you've shared a lot of knowledge on biocatalysis and much more, so thank you very much. We'd obviously like to thank our sponsor again, Johnson Matthey, and just to remind the audience, if you missed anything, you want to go back and listen again, then you're going to get a recording of the webinar emailed out to you in a couple of days. So if you registered and you're here, you can watch it again, and you can also share that with anyone that you know who might be interested. And finally, a big thank you to our audience. We had a lot of you on the call today, a lot of interest here in this subject, which is brilliant to hear, and you've asked some fantastic questions. So if you've enjoyed this webinar, then please do check out chemistryworld.com/webinars for future events. And while you're there, feel free to register for a Chemistry World account, where you can even sign up to our very popular Reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. And that's it from us, from everyone here at Chemistry World. We look forward to seeing you again in a future webinar. Thank you very much.